Okay, for 2013, we have number one gives us a rate function, tons per hour. Unprocessed gravel arrives at a gravel processing plant. We're given the G function. Time frame is 0 to 8, including both endpoints. Beginning of the workday, the plant has 500 tons of unprocessed gravel, and the hours of operation are 0 to 8. And the plant processes gravel at a constant rate of 100 tons per hour. Okay. So again, this is the function that tells us how the gravel is arriving at the plant. Okay, and they're processing the gravel at a constant rate of 100 tons per hour. So, with that said, the part A says to find G prime at 5. So if we want G prime at 5, we would need G prime first, or not, because what we want to recognize here is that this is a derivative at a point problem. We have it's a calculator problem. We have G, and we just want the derivative at 5. That makes it an undir problem. We don't need to take time finding the derivative of that and then plugging 5 in there. We can just go ahead and use our math 8 as our derivative command. And if we use the function 90 plus 45 cosine, one thing that you want to make sure you do here is check and make sure you're in radian mode. They're very unlikely going to be a problem that you need to be in degrees, so make sure your calculator's in radians. So cosine x squared over 18, comma x, comma 5, and the derivative is negative 24.588. Once again, make sure you round to the nearest 3 decimal places. Okay, on the test that you guys did, still got rounding errors. Okay, 3 decimal places. Not 4, not 5, not 2, not 1, 3. Okay, 3 decimal places unless it tells you otherwise. Okay, point breakdown for that. I didn't finish the units part here yet, but ultimately the answer, of course, is this negative 24.588. You get a point for that. And then they want us to say using correct units, interpret what we got there. So keep in mind that if G was measured in tons per hour, and we're finding the derivative of that. Keep in mind a graph that's tons per hour versus hours, and we find the slope of it. Okay, at a point, we're going to be doing the y-coordinates divided by the x-coordinates. It's kind of like an acceleration, isn't it? Okay, so we'd say this is in tons per hour squared. Whoops, tons per hour squared would be the units. Okay, and ultimately this is the rate at which the gravel is arriving. Okay, we could say it's decreasing at that point. Okay, the rate is decreasing, we'd say, not the amount of gravel, the rate we're talking about, because remember G is a rate here, so if we explain that, we'd say the rate at which the gravel is decreasing is the negative 24.588 tons per hour squared. Okay. All right. And another point for that, so two altogether. Part B says find the total amount of unprocessed gravel that arrives at the plant during the hours of operation on this workday. Okay, so the total amount of unprocessed gravel that arrives. So we don't really care about the actual processing part. We just want to know how much is going to arrive. And we know that if G of T is in tons per hour versus hours, the area under that curve is going to give us tons, which is exactly what we want. So if we write an integral from 0 to 8 of G of T dt, and once again, it's a calculator problem, so if we do our integral command, should be 825.551 tons. And they gave 2 points for that. 1 if you got the integral right, and 1 if you got the answer. Part C says, is the amount of unprocessed gravel at the plant increasing or decreasing at time 5? Okay, and show the work that leads to your answer. Okay. Ultimately, we want to know, we need to compare the rates at which we're having gravel arrive and the rate at which we're getting gravel processed. Okay? And if you do G of 5, okay, this would give us the rate at which the stuff is arriving. Okay? So if we do 90 plus 45 cosine of 5 squared over 18, okay. Again, it's a calculator problem, turns out to be 98.140764, etc. And with that said, okay, that's the rate at which we have gravel arriving. Okay, the rate at which the gravel is leaving, if you will, and leaving by that I mean it's being processed, so it's going to be taken care of. Okay, that rate is 100. So that means that it's coming in at this rate, it's going out at this rate, so that means that the amount of gravel is doing what? It's decreasing. It's coming in at a slower rate than it's going out. Okay, so if we're the processors, we're actually making some headway at this point, right? We're processing more gravel than it's coming in at that point. Okay, so we can say that since that 98.141 is less than 100, okay, the amount of gravel is decreasing at that point in time. Okay, they awarded 2 points for that. One for finding the two rates and making the comparison, and then one for drawing the conclusion that since this one is less than 100, and the amount is decreasing at that point in time. Okay. All right. Then in part D, it says that what is the maximum amount of unprocessed gravel at the plant during the hours of operation on this workday? Okay. So we want the maximum amount of unprocessed gravel at the plant during the hours of operation on the workday. So keep in mind again that it's 0 to 8. Okay. So I would make a candidate test problem out of it. Okay. So we're looking for the amount of gravel at these given times. Let's take care of the endpoints first. At time 0, there's 500 tons. Okay, they told us that. That was given in the problem. Okay, at time 8, we need to figure out how much unprocessed gravel there is at time 8. So keep in mind that to figure that out, we're going to need to, let's just call it A, if you will. Okay, so A of T, we'll call it the amount of gravel. There would be 500 to start the day. There would be 0 to T of our G function. Okay, that would add the amount that's arriving at any given time. And then if I did 100 T subtracted from that, okay, that would take away the right amount of gravel for any given time then, wouldn't it? Okay, so that would be my amount equation, so that would tell me my amount of gravel at any given time. And so if we want to figure that out, we're going to put an 8 in there. So we'll do 500. And then keep in mind that we already did the integral part from 0 to 8 up here. So we'll have 500 minus that, 825.551. And then minus, nope, that's added, sorry. Add that. We're adding that much to the gravel. And then we're also subtracting 800, because we will have processed 100 times 8, 100 per hour for 8 hours. And so that amount at the end of the day is going to be 525.551. So far that's the leader, because we're looking for a maximum, it said. And then the other part's going to come from A prime at T being equal to 0. So if we do A prime here, that's going to be G of X, or G of T I should say, minus 100. Okay. So that derivative would equal 0. If we set that equal to 0, we would want to know when 100 is equal to G of T. Well, we have the G function. So if we set that equal to 100 and solve it, turns out it's 4.923. Okay. And if we go ahead and put 4.923 into our equation to figure out the amount, 500 plus the integral of our 90 plus 45 cosine x squared divided by 18. And then we go from 0 to 4.923. I would probably use as many decimals as I can in decimal places in the integral, of course, so we don't have rounding errors. It turned out to be 9.2348. Okay. Right. And then if we subtract off 100 times 4.92348, That should give us the amount at that time. Turns out to be 635.376. And with that said, we can see that that's going to be the maximum amount right there. That's bigger than any of the other two, the endpoints, if you will. So we'd say that, just like it says here, the maximum amount of unprocessed gravel at the plant during the workday is 635.376 tons. And again, they asked us for the maximum amount. They didn't ask us for when it occurs. That obviously would be part of your work here, but to answer the question, we want to make sure we tell how many tons, like they asked. If you set the derivative equal to 0, they gave you a point. Okay. If you found the right answer, you got another point, and your justification is the candidate test. Okay. So when it says justification, okay, you really don't have to write anything more to it other than just showing your work on the candidate test. Okay. So anytime it's a closed interval, okay, we're going to use that candidate test. Questions so far? Alright, the next one says a particle moves along a straight line, got a velocity curve given. Says the position is S, we know the initial position. And in part A it says find all the values on the interval 2 to 4 for which the speed of the particle is 2. Okay. So we want the speed of the particle to be 2, knowing that our velocity curve is -2 plus t squared plus 3t to the 6/5 minus t cubed. Okay. And once again, we want the speed to be equal to 2. So knowing that it's a calculator problem, I would take the absolute value of that expression, okay, set it equal to 2, and then I would solve that with a calculator. Okay. No good reason to try to do this with algebra. So if we set that equal to 2, turns out to be 2 different times, 3.128 and also 3.473. The 2 points in question. So if you recognize that the velocity's absolute value is the speed, and you set that equal to 2, you got a point. And if you put that in your calculator and found the intersection points, okay, you would have gotten the second point. So 2 points total. Part B says we're going to write an expression involving an integral that gives the position S of t, and use this expression to find the position of the particle at time 5. So our S of t function, remember, is going to come from the integral of the velocity function. Alright. The other thing that we got to consider here too, though, is that the initial position is 10. So we'd want to put a 10 plus out in front. 0 to t of -2 plus x squared plus 3x to the 6/5 minus x cubed. Okay. So that expression right there would give us the position at any time. Gives us the initial position plus the displacement. That gives us our position at any time. Okay. So the point breakdown are going to be as follows. If you got the expression correct, okay, you got a point. And then they asked us to use this expression to find the position of the particle at time 5. So of course we're just going to plug a 0 to 5 in there of our v of x function, and it turns out to be -9.207. So the position at that time. Question so far? Okay, then part C says find all the times on the interval 0 to 5 at which the particle changes directions. Okay, we know that it's going to change directions anytime the velocity equals 0. So if you set the velocity equal to 0 and find the 2 intersection points there that are between 0 and 5, should be these figures, 0.536 and 3.318. Okay, get a point for setting the derivative equal to 0. And then the other thing you got to consider here too is that do we really change directions at both of those points? Okay, so if I were you, I would make a number line, keeping in mind that the time frame is 0 to 5 here. 2 points in question are 0.53, 0.536, and then also 3.318. And if we do a number line test here for the velocity, okay, to see if the velocity does in fact change, we know even if the velocity is 0, it might not change from negative to positive, which means it wouldn't be a change of direction. It would just stop and then go forward again or backward, whatever the case may be. And it turns out if we do the test here, okay, it says V of t changes sign from negative to positive at that. So that just time frame wise, I'll just go ahead and trust their analysis here. But if you plug the test point into the velocity, you'd get negative here, positive here, and it changes from positive to negative at that other point. Whoops, positive to negative. So this would show that we do in fact change directions at both of those points. Okay. All right. So we do change directions at 0.536 and also at 3.318. And therefore we get 2 more points. If we set the derivative equal to 0, find those points, we got a point. And if we indicated that there was a change of direction in y, okay, we got 2 more points for that, so 3 total there. Okay. All right, and then finally, the question on part D is the speed of the particle increasing or decreasing at time 4. So remember, what we want to know then is what are the velocity and the acceleration like. Okay, we've seen this problem several times now. If the velocity and the acceleration have the same sign, we're going to say the speed is increasing. If the velocity and acceleration have different signs, then we're going to say the speed is decreasing. So the velocity at 4 turns out to be negative 11.476. Again, just trusting their math. Okay. The acceleration is negative 22.296. So that means that if the signs are the same on those two, okay, the answer is increasing because both of them are less than 0. Okay. And keep in mind, the picture of that means that the velocity is negative. If we drew the velocity curve, negative and decreasing, because the acceleration being negative. Whether it's concave up or concave down, it does not matter, because in both cases the speed, okay, which is the absolute value of these two curves, okay, is going to be increasing. Okay. So 2 more points for that. You figured out the 2 numbers in question, that they're both negative, and said that the speed was increasing. We got the 2 points there.